Welcome to Universe Orbit, your gateway to exploring the vast wonders of space, where the mysteries of the cosmos unfold through captivating videos. Don't forget to subscribe so you never miss a single voyage through the infinite universe. The Sun, an immense ball of incandescent gas, lies at the very center of our solar system, serving as both its engine and its anchor. It is a star like countless others scattered across the universe, yet its proximity to Earth and its vital influence on our planet make it profoundly unique. This stellar giant, glowing with an intensity that can be sensed even from millions of kilometers away, provides the light and heat that sustain life on Earth, governs the motions of planets, and shapes the very environment of our cosmic neighborhood. Understanding the Sun is to understand the heartbeat of the solar system, the invisible force that binds planets, asteroids, comets, and countless other celestial bodies into a harmonious, dynamic system. The Sun's existence and activity dictate the rhythms of life and the passage of time on our planet. Its light determines day and night, its warmth the seasons, and its gravitational pull maintains the orbital ballet of planets that dance around it in predictable yet astonishingly complex paths. The Sun is composed primarily of hydrogen and helium, two elements forged in the heart of the cosmos long before our solar system even existed. Hydrogen dominates its composition, forming about 3/4 of its mass, while helium accounts for nearly 1/4. The remaining fraction consists of heavier elements, including oxygen, carbon, neon, and iron, which play subtle but crucial roles in the Sun's internal dynamics. At the Sun's core, the intense pressure and temperature reach extraordinary levels, over 15 million degrees Celsius, hot enough to fuse hydrogen nuclei into helium through nuclear fusion. This process releases an enormous amount of energy in the form of light and heat, which gradually makes its way outward through the Sun's layers, eventually escaping into space as the radiant sunlight that bathes Earth. Nuclear fusion is the source of the Sun's energy, and it is remarkable not only for its sheer power, but also for its efficiency, converting tiny amounts of matter into energy according to Einstein's famous equation, E=mc². The energy produced in the Sun's core has been streaming outward for billions of years, sustaining the delicate balance of life on Earth while slowly altering the Sun itself over cosmic timescales. The structure of the Sun is divided into several distinct layers, each with its own physical characteristics and functions. The innermost region is the core, where fusion occurs and energy is generated. Surrounding the core is the radiative zone, where energy travels outward primarily as photons, bouncing countless times in a slow, tortuous journey that can take thousands of years to reach the next layer. Beyond the radiative zone lies the convective zone, where energy is transported by the rising and falling currents of hot plasma. This movement creates a churning surface and contributes to magnetic activity that eventually manifests as sunspots, solar flares, and coronal mass ejections. Above the convective zone lies the photosphere, the visible surface of the Sun, which emits the light we see with our eyes. It appears as a glowing yellow-white disk in the sky, though in reality, it is only about 500 kilometers thick, a thin veil compared to the Sun's enormous diameter. Beyond the photosphere are the chromosphere and the corona, layers of the Sun's atmosphere that are less dense but remarkably hot, with the corona reaching temperatures of over 1,000,000 degrees Celsius. These outer layers are the source of solar winds, streams of charged particles that flow outward and influence the entire solar system, interacting with planetary magnetic fields and shaping phenomena like auroras on Earth. The Sun is not a static body, it is dynamic and constantly changing. One of the most observable aspects of its variability is the solar cycle, which lasts about 11 years on average. During this cycle, the number of sunspots, dark regions on the Sun's surface caused by intense magnetic activity, rises and falls. Sunspots are often associated with solar flares and coronal mass ejections, violent eruptions that release tremendous amounts of energy and particles into space. These events can have profound effects on Earth, disturbing satellites, communication systems, and even electrical grids. Solar activity is thus not merely a distant curiosity. It directly impacts human technology and life, highlighting the sun's role as an active, influential force in the solar system. Studying the sun's behavior is essential not only for understanding our own planet's environment, but also for preparing for the broader challenges of space exploration, where solar radiation and energetic particles can pose serious hazards to astronauts and spacecraft. Beyond its immediate influence on Earth, the sun's gravity holds the solar system together, dictating the orbits of planets, moons, asteroids, and comets. Without the sun's gravitational pull, planets would drift into the void of space, and the delicate balance of forces that allows life to flourish on Earth would collapse. Each planet orbits the sun in a nearly elliptical path, a motion described by the laws of planetary motion discovered by Johannes Kepler in the 17th century. The sun's mass is so immense, more than 300,000 times that of Earth, that it dominates the solar system, accounting for more than 99.8% of its total mass. Its gravitational influence extends far beyond the orbit of Pluto, shaping the trajectories of comets from the distant Oort cloud and sending icy wanderers on spectacular journeys into the inner solar system. The sun thus acts as both a nurturing center and a powerful anchor, maintaining the order and structure of the celestial system that surrounds it. The sun's light and heat are critical drivers of life on Earth. Photosynthesis, the process by which plants convert sunlight into chemical energy, forms the foundation of the planet's food chains. Without sunlight, ecosystems would collapse, temperatures would plummet, and life as we know it would be impossible. The sun also influences climate, weather patterns, and ocean currents, shaping the environment in complex and interconnected ways. Over longer periods, changes in the sun's output have contributed to ice ages and periods of warming, underscoring the delicate balance between solar energy and Earth's climate systems. The study of these interactions, a field known as solar terrestrial physics, reveals the deep connection between the sun and the environment of our planet, reminding us that we are intimately linked to the rhythms and energy flows of our star. Solar observation has fascinated humans for millennia, inspiring myths, calendars, and early astronomical studies. Ancient civilizations such as the Egyptians, Mayans, and Greeks revered the sun as a deity, recognizing its life-giving properties and its predictable motions across the sky. The invention of the telescope allowed astronomers to study the sun in unprecedented detail, revealing sunspots, solar flares, and the complex structures of its atmosphere. Modern solar observatories, both on Earth and in space, provide continuous monitoring of the sun, capturing high-resolution images and measuring magnetic fields, particle emissions, and other phenomena. Space missions such as the Solar and Heliospheric Observatory, SOHO, Parker Solar Probe, and Solar Orbiter have brought humanity closer than ever to understanding the sun's intricate behavior, revealing its influence not just on Earth, but on the entire solar system. These observations deepen our knowledge of stellar physics, helping us comprehend the life cycles of stars and the processes that govern their energy output and longevity. The sun is also a key to understanding the broader cosmos. By studying its composition, behavior, and life cycle, scientists gain insights into the nature of stars throughout the universe. The sun is a middle-aged star, approximately 4.6 billion years old, with an estimated total lifespan of about 10 billion years. This means it is currently in a stable phase of hydrogen fusion, known as the main sequence, a period during which it steadily emits energy and maintains equilibrium between gravitational collapse and outward pressure from fusion. Eventually, as hydrogen in its core is depleted, the sun will evolve into a red giant, expanding dramatically and potentially engulfing the inner planets, including Earth. After shedding its outer layers, it will leave behind a dense, cooling remnant known as a white dwarf, a final stage that illustrates the destiny of many stars in our galaxy. Understanding this life cycle provides a window into the processes that govern stellar evolution, planetary system formation, and the long-term fate of our solar neighborhood. The sun's magnetic field is another fascinating aspect of its complexity. Generated by the movement of charged particles in its convective zone, the sun's magnetic field extends far into space, shaping the heliosphere, a vast bubble that encloses the entire solar system. This magnetic influence protects planets from cosmic radiation, channels the solar wind, and drives spectacular auroras near the poles of planets with atmospheres and magnetic fields. Magnetic reconnection events, where the sun's magnetic field lines snap and realign, release vast amounts of energy and are responsible for solar flares and coronal mass ejections. The intricate dance of magnetic fields on the sun is a source of continuous scientific investigation, as understanding these processes is crucial for predicting space weather and mitigating its effects on technological infrastructure and human space travel. The study of the sun also intersects with questions about the origins of the solar system itself. The sun formed from a giant molecular cloud, a region of space filled with weight and dust, collapsing under its own gravity. As the cloud contracted, conservation of angular momentum caused it to spin, forming a rotating disk around the nascent sun. Within this protoplanetary disk, particles collided and coalesced to form planets, moons, asteroids, and comets, a process that eventually gave rise to the solar system as we know it today. By studying the sun and its early development, scientists gain insights into the conditions that foster planet formation, the distribution of elements within a star, and the processes that shape planetary systems across the galaxy. The sun is thus both a product of cosmic evolution and a catalyst for the complex systems that orbit it, linking the story of our planet to the broader narrative of the universe. The sun's influence extends beyond the confines of the solar system. Solar wind, composed of charged particles streaming outward, interacts with the interstellar medium, forming a protective bubble that shields the solar system from some of the galaxy's high-energy radiation. This heliosphere is critical for maintaining a stable environment within which planets can host atmospheres and, ultimately, life. Additionally, by comparing the sun to other stars, astronomers can identify similarities and differences that inform the search for exoplanets and habitable systems. Understanding how the sun generates and distributes energy, how its magnetic field interacts with surrounding space, and how its life cycle unfolds allows scientists to better comprehend the conditions necessary for life elsewhere in the universe. The sun, in this sense, is a local laboratory for stellar physics, a benchmark for understanding stars throughout the cosmos, and a source of inspiration for humanity's quest to explore the universe. Even as humanity ventures deeper into space, the sun remains a central figure in our understanding of the cosmos. Solar observations guide missions to the Moon, Mars, and beyond, providing critical data on radiation hazards, energy sources, and orbital dynamics. Solar energy, harnessed through advanced technology, powers spacecraft, satellites, and even potential habitats on other worlds, emphasizing the sun's practical importance for exploration and colonization. In addition, the sun's predictable cycles allow for precise navigation, timing, and communication, reinforcing its role as a reliable cosmic reference point. As our technological capabilities expand, our reliance on the sun's energy, gravitational guidance, and magnetic shielding continues to grow, highlighting the inseparable bond between our star and the flourishing of human civilization. The sun inspires not only scientific inquiry, but also artistic, philosophical, and spiritual reflection. Its radiant presence in the sky has been a symbol of power, renewal, and continuity for countless cultures. Sunrises and sunsets evoke wonder and contemplation, reminding humanity of the scale, beauty, and rhythms of the universe. The sun's constancy, despite its ever-changing surface phenomena, provides a sense of stability in an otherwise vast and unpredictable cosmos. Artists, poets, and thinkers have long celebrated its brilliance, using its light as a metaphor for knowledge, hope, and life itself. The sun thus occupies a unique place not only in the scientific study of the cosmos, but also in the human imagination, bridging the gap between empirical observation and the profound emotional experience of the natural world. As we look toward the future, the sun will continue to shape our understanding of the universe and our place within it. Advanced solar observatories, increasingly sophisticated models of stellar behavior, and missions that bring spacecraft ever closer to the sun promise to reveal new layers of complexity and beauty. The study of solar physics intersects with pressing challenges on Earth, from climate change to sustainable energy, while also supporting the long-term ambitions of space exploration. In every sense, the sun is the heart of our solar system, a dynamic, life-giving, and awe-inspiring star whose influence extends from the innermost layers of its own structure to the farthest reaches of interstellar space. Its energy fuels life, its gravity orchestrates planetary motions, and its magnetic fields sculpt the very environment through which we travel. Understanding the sun is, ultimately, to understand the fundamental forces that govern the solar system, the delicate balance that sustains life on Earth, and the cosmic processes that shape our universe. The sun's magnetic phenomena are among the most fascinating aspects of its dynamic nature. Sunspots, first recorded by ancient astronomers, are cooler regions on the sun's surface caused by intense magnetic activity, appearing as dark blotches against the bright photosphere. These spots are not merely cosmetic. They are indicators of powerful underlying processes. The number and distribution of sunspots fluctuate according to the solar cycle, an approximately 11-year rhythm during which the sun's magnetic field gradually reverses. This cycle influences solar radiation, solar wind intensity, and the frequency of solar storms, creating cascading effects throughout the solar system. Solar flares, sudden bursts of electromagnetic energy associated with magnetic reconnection events, can release energy equivalent to millions of nuclear bombs in a matter of minutes. Coronal mass ejections, colossal expulsions of plasma and magnetic field can travel millions of kilometers into space, interacting with planetary magnetospheres and causing geomagnetic storms on Earth. The study of these phenomena is not only of academic interest but of practical importance, as modern civilization's reliance on satellites, communication systems, and power grids makes it vulnerable to disruptions caused by space weather. The sun's impact on planets extends far beyond Earth. Mercury, the closest planet to the sun, experiences extreme temperatures and intense solar radiation that shape its barren, cratered surface. Venus, enveloped in a thick atmosphere, is subject to solar-driven winds and ultraviolet radiation that contribute to its runaway greenhouse effect. Mars, with its thin atmosphere and weak magnetic field, is particularly vulnerable to solar wind stripping, a process that may have played a role in the planet's loss of surface water over billions of years. The outer planets, while more distant, are not immune. Jupiter's massive magnetosphere interacts with the solar wind in complex ways, generating auroras and shaping its radiation environment. Saturn, Uranus, and Neptune experience similar influences, though their distances and compositions modulate the effects. Even the distant objects of the Kuiper Belt and the Oort cloud are subtly affected by the sun's gravitational pull and radiation pressure, highlighting the star's far-reaching influence across the solar system. Understanding the sun is also essential for interpreting its past and predicting its future. Observations of solar analogs, stars similar in size, composition, and age, allow scientists to model the sun's evolution and anticipate changes that could affect Earth and neighboring planets. As the sun gradually exhausts hydrogen in its core, it will transition into a red giant phase, expanding its outer layers and potentially engulfing Mercury, Venus, and even Earth. This transformation will dramatically alter the conditions of the solar system, reshaping planetary surfaces and atmospheres. Eventually, the sun will shed its outer layers, forming a planetary nebula, leaving behind a white dwarf that will slowly cool over billions of years. Understanding this life cycle is crucial for grasping not only the long-term fate of our planet, but also the processes that govern stellar evolution and the formation of new planetary systems in the galaxy. The historical study of the sun has been a journey of observation, theory, and discovery. Early civilizations used the sun's predictable motion to develop calendars, agricultural cycles, and religious rituals. The ancient Egyptians aligned pyramids and temples with solar positions, while the Mayans constructed observatories to track solstices and equinoxes. In the Renaissance, telescopic observations revealed sunspots, challenging the notion of an unchanging, perfect celestial sphere. The development of spectroscopy in the 19th century allowed astronomers to analyze the sun's composition, revealing the presence of elements such as hydrogen, helium, and trace metals. In the 20th and 21st centuries, space-based observatories revolutionized our understanding, providing continuous, high-resolution observations free from atmospheric distortion. Missions like SOHO, SDO, Solar Dynamics Observatory, Parker Solar Probe, and Solar Orbiter have revealed the intricate structure of the corona, the dynamics of solar wind, and the subtle interplay of magnetic fields, transforming the study of solar physics into a precise, predictive science. The sun's role in climate and environmental systems on Earth is another vital area of study. Variations in solar output, though relatively small compared to human-induced climate changes, can influence long-term patterns such as the Little Ice Age or periods of warming in Earth's history. Solar radiation drives atmospheric circulation, ocean currents, and weather patterns, creating complex feedback loops that scientists continue to unravel. The study of solar-terrestrial interactions helps in modeling climate systems, predicting space weather, and planning for the effects of solar variability on technology, agriculture, and infrastructure. Moreover, understanding how the sun's energy is absorbed, reflected, and redistributed by Earth's atmosphere and surface is fundamental to addressing contemporary challenges such as global warming, renewable energy generation, and sustainable resource management. The sun is also central to the exploration of space and the development of future technologies. Solar energy provides a nearly limitless source of power for satellites, space stations, and spacecraft venturing beyond Earth. Concepts for solar sails, which use the pressure of sunlight to propel spacecraft, harness the sun's energy in innovative ways, demonstrating the star's role not just as an observational subject, but as a practical resource for space exploration. Human missions to the Moon, Mars, and beyond rely on accurate models of solar radiation and particle flux to protect astronauts from harmful exposure. As humanity prepares for long-duration space travel, understanding the sun's behavior becomes crucial for survival, health, and the operation of life support systems. The sun thus remains not only a celestial object of wonder, but a practical factor in the ongoing expansion of human presence into the cosmos. Cultural and philosophical perspectives have long intertwined with the study of the sun. Its prominence in human consciousness has inspired art, literature, and spiritual reflection. Ancient myths often portrayed the sun as a deity, a chariot racing across the sky, or a source of wisdom and illumination. In literature, the sun symbolizes knowledge, clarity, and renewal, while in art it represents vitality, hope, and the passage of time. The daily rise and fall of the sun creates a rhythm that humans have historically aligned with life, work, and ritual, embedding the star deeply into cultural consciousness. The scientific understanding of the sun has not diminished its symbolic power. Rather, it has enriched it, allowing humanity to marvel at both its physical intricacy and its metaphorical resonance. The sun is a reminder that science and culture, observation and imagination, coexist in shaping human experience and understanding. The sun's influence also extends into the study of astrobiology and the search for life beyond Earth. By understanding the conditions the sun provides for habitability, scientists can identify other stars with the potential to host planets capable of supporting life. The concept of the habitable zone, the region around a star where liquid water could exist on a planetary surface, is directly tied to the sun's energy output. Studying the sun's radiation, magnetic activity, and variability helps define the parameters that make Earth uniquely suited for life and guides the search for exoplanets in similar circumstances. This research underscores the importance of the sun not only as a provider of energy and gravitational structure, but also as a benchmark for understanding the requirements for life in the universe. Our star is a laboratory in which the principles of habitability, planetary protection, and cosmic evolution can be explored and understood. The sun is a source of constant scientific fascination because of the complex interplay of physical forces it exhibits. Its rotation, differential in nature, causes the equator to spin faster than the poles, twisting magnetic field lines and generating dynamic solar activity. Plasma flows within the convective zone create giant convection cells, driving turbulence that shapes sunspot formation and magnetic cycles. Helioseismology, the study of oscillations within the sun, allows scientists to probe its interior, revealing details of density, temperature, and motion hidden beneath the visible surface. These studies enhance our understanding of fundamental physics, from nuclear reactions to magnetohydrodynamics, and provide insights applicable to other stars, fusion research, and even energy technologies on Earth. The sun, therefore, is both a natural wonder and a scientific laboratory, offering endless opportunities to expand knowledge and inspire curiosity. Even as we delve into these intricate phenomena, the sun remains an accessible and constant presence in daily life. Its light defines the passage of time, from the warmth of morning rays to the fiery hues of sunset. Seasons are marked by its changing angles in the sky, and its energy fuels ecosystems, agriculture, and human activity. Ancient calendars, modern clocks, and even solar-powered devices all rely on this steadfast celestial engine. The sun's predictability, combined with its dynamic complexity, makes it a cornerstone of human experience, both practically and philosophically. It reminds us of the delicate balance that sustains life and the grandeur of cosmic forces that operate on scales far beyond human comprehension. In studying the sun, humanity is both seeking knowledge and in reflecting on its own connection to the broader universe. Solar energy is perhaps the most tangible gift the sun provides to Earth. The photons that reach our planet carry immense amounts of energy, which drives the climate, weather, and life cycles. Plants convert sunlight into chemical energy through photosynthesis, forming the foundation of virtually every ecosystem. This energy eventually moves up the food chain, supporting herbivores, carnivores, and omnivores alike. Beyond biology, solar energy is increasingly harnessed through human technology, from photovoltaic cells generating electricity to concentrated solar power plants supplying heat and energy. Innovations in solar technology aim to capture this energy more efficiently, storing it for use during nighttime or cloudy periods, and integrating it into sustainable energy strategies to reduce reliance on fossil fuels. In essence, the sun's energy sustains life in natural systems, empowers human civilization in profound ways, linking the biological, technological, and societal realms in a continuous cycle of influence. The sun's role in the formation and evolution of the solar system is another critical dimension of its significance. Approximately 4.6 billion years ago, a giant molecular cloud began to collapse under gravity, triggering the birth of the sun. As the proto-sun formed at the center, a rotating disk of gas and dust surrounded it, serving as the nursery for planets, moons, asteroids, and comets. Material in this protoplanetary disk collided, accreted, and gradually coalesced into the bodies we observe today. The sun's gravitational pull dictated the structure of orbits, while its radiation and solar wind cleared away remaining gas and dust, shaping the final architecture of the solar system. The sun's early activity also influenced planetary atmospheres, the distribution of volatile elements, and even the potential for habitable conditions on Earth. Understanding the sun's formation and early behavior provides crucial context for the origin of the solar system, the diversity of planetary environments, and the processes that produce habitable worlds across the galaxy. Comparative stellar astronomy offers further insight into the uniqueness and universality of the sun. By studying stars of different sizes, compositions, and ages, astronomers place the sun within a broader cosmic context. It is classified as a G-type main sequence star, or G-dwarf, which is relatively stable, long-lived, and moderately luminous. This classification explains why the sun has provided a steady source of energy for billions of years, allowing life to emerge and evolve on Earth. Observations of other G-type stars and their planetary systems help scientists predict solar behavior, understand stellar evolution, and refine models of planetary habitability. While the sun is a typical star in many respects, its combination of stability, proximity, and size makes it uniquely influential for the development of complex life on the orbiting planets, particularly Earth. Space missions dedicated to studying the sun have revolutionized our understanding and continue to reveal new phenomena. The Solar and Heliospheric Observatory, SOHO, has provided continuous observation of the sun's surface and atmosphere for decades, capturing sunspots, flares, and coronal mass ejections in unprecedented detail. The Parker Solar Probe, launched in 2018, is making history by traveling closer to the sun than any previous spacecraft, directly sampling the solar corona and solar wind. Solar Orbiter, a mission by the European Space Agency, studies the sun's polar regions, helping scientists understand magnetic field generation and solar cycles. These missions, combined with Earth-based observatories and advanced computer modeling, allow researchers to probe questions that were once unimaginable. How the corona reaches temperatures far exceeding the surface, how solar storms are triggered, and how energy is transported through the sun's interior. Each discovery deepens our knowledge of fundamental physics while directly informing our understanding of Earth's environment and technological vulnerabilities. Solar phenomena extend beyond sunspots and flares to include spectacular events like prominences, filaments, and coronal loops. Prominences are massive arcs of glowing plasma suspended above the sun's surface by magnetic fields, sometimes stretching hundreds of thousands of kilometers into space. Filaments, seen as dark strands against the photosphere, are the same structures viewed from a different perspective, highlighting the sun's dynamic three-dimensional complexity. Coronal loops, shaped by magnetic field lines, trace the pathways of hot plasma in the solar atmosphere, illustrating the intricate interaction of magnetic forces, pressure, and temperature. The heating of the corona to temperatures exceeding 1,000,000 degrees Celsius remains one of the enduring mysteries of solar physics, prompting investigation into wave heating, magnetic reconnection, and particle acceleration. Understanding these phenomena is not merely an academic pursuit. It has practical implications for predicting solar storms and safeguarding Earth-based and spaceborne technology. The long-term implications of the sun's activity are profound for Earth and human civilization. Solar variability, both in the short term with flares and in the long term with gradual changes in luminosity, can influence climate, agriculture, and energy systems. Historical records suggest correlations between periods of low sunspot activity, such as the Maunder minimum, and cooler global temperatures. In the context of modern climate science, understanding the sun's contributions allows for more accurate modeling of natural versus anthropogenic climate influences. Moreover, as humanity ventures into space, anticipating solar particle events and radiation bursts becomes critical for astronaut safety, mission planning, and the design of protective shielding. The sun, in this sense, is both a source of life-sustaining energy and a force capable of significant disruption, reinforcing the need for continuous study and preparedness. The sun also provides a profound perspective on time, scale, and the interconnectedness of cosmic processes. The photons that illuminate Earth today may have been generated in the sun's core thousands or even millions of years ago, traveling a slow, tortuous path through radiative and convective layers before escaping into space. The solar wind, traveling at millions of kilometers per hour, carries the sun's magnetic influence across billions of kilometers, connecting the inner planets with the distant edges of the heliosphere. Light and particles from the sun-shaped planetary atmospheres drive auroras and influence the space environment throughout the solar system. In observing and understanding these processes, humanity gains insight not only into our star, but into the fundamental forces that govern the universe: gravity, electromagnetism, nuclear fusion, and plasma dynamics. The sun becomes a lens through which we view the complex web of interactions that define the cosmic environment and our place within it. Finally, the sun is a source of inspiration, curiosity, and humility. Its immense scale, power, and complexity remind us of the vastness of the cosmos and our relatively small place within it. Yet its proximity and comprehensibility make it a subject of deep scientific inquiry, a natural laboratory for studying phenomena that occur throughout the universe. The sun's light illuminates our skies, sustains life on Earth, and drives the cycles of nature, technology, and human endeavor. Its study has transformed our understanding of physics, astronomy, and planetary science, while also enriching culture, art, and philosophy. The sun is more than a star. It is the heart of the solar system, the engine of life, and a symbol of continuity and change, stability and dynamism. Its influence permeates every aspect of our world, from the tiniest photosynthetic cell to the orbits of planets, and from ancient myths to modern space exploration. In every way, the sun stands as a reminder of the intricate, interconnected, and awe-inspiring universe in which we live. The journey of understanding the sun is ongoing, and as technology advances, new missions will probe its mysteries, revealing layers of complexity yet unseen. Scientists continue to explore the mechanisms of magnetic reconnection, the processes behind coronal heating, the behavior of solar wind, and the intricate interplay between solar cycles and planetary climates. Each discovery not only deepens our scientific knowledge, but also enhances our capacity to live sustainably on Earth and venture safely into space. By studying the sun, humanity touches the core of the solar system, unlocking insights that connect the past, present, and future of our planet, our solar neighborhood, and the universe at large. The sun, in its brilliance, serves as both a source of life and a guide for exploration, a celestial anchor and a cosmic teacher, forever central to the story of the solar system and the ongoing quest to understand our place among the stars.